Alright, 10.3 video notes, volume of prisms and cylinders. So on 10.1 and 10.2 we were basically trying to figure out the surface area, how much material it took to build these three-dimensional solids. Now we're concerned about how much stuff can we put inside there, how much can it hold, whether it be a liquid or a solid, or so a lot of packaging implications for engineering. And the formulas today aren't too bad, so let's go ahead and let's just jump right into this. Um, so most of these are all pretty much the same, and the common idea is basically this. The volume of a prism is the area of the base multiplied by the height. So you always want to figure out what is the area of the base, which would be this red triangle, and then you're going to multiply it by how high it goes. So that's pretty much it for all prisms and cylinders. Now, so notice that there's a capital B. So like a lot of times when we do the area of a rectangle, we'll write this as, little base times height. Well, they're using capital B to represent the base area. All right, so sometimes instead of using that, I'm going to say base area times the height, just because I think it's a little better than just using the B. So that's just something I'm going to do. For rectangular prisms or boxes, you can also just use this formula, which is probably what you learned, more in grade school. Volume is just length times width times height. But if you really break it down, length times width is actually the base area. That's your base area. So this LW is really just BA, and then you multiply by the height. But it's faster to just kind of multiply all three together and kind of do it that way. Now a cube is special because it's a rectangular prism that has all equal sides. So when you do, and they're calling the side S, when I do the base area, I get S times S, which would give me this area, which is S squared. And then when you multiply by another dimension of S, they come up with S to the third. So, really all three of these formulas right here, they're all the same. They're pretty much all base area times height. It's just sometimes you can write them a little bit differently. I'm going to treat them pretty much all the same. Now moving on to a cylinder. Cylinders are the same exact idea. Same setup. If you can think of base area times height, it's just now our base area is a circle. The area of that base is pi r squared, and then we're going to multiply it by how high it goes. So the volume for a cylinder is just pi r squared h, or base area times height. So today should flow pretty easy. I find volume a lot easier than surface area. I think it's a much easier calculation, so these ones shouldn't be too bad. So let's jump into our examples. So example 1, looks like we have a rectangular prism. So this is a rectangular prism, otherwise known as just a box. So I'm just going to use the length times width times height. So I'm going to do 16 multiplied by 4 multiplied by 9. So that's 64 times 9. That'd be 540 and 36. I believe it's 576. Let me grab a calculator here and double check that. 16 times 4 times 9. 576. Now, units. Let's talk about units a little bit. Units are basically cubed. Area had square units. This is centimeters to the third, or I could say 576 cubic centimeters. And this is kind of important because basically what we're doing in this picture, there's a lot of them. I'm going to kind of draw a picture that's a little bit easier to understand here. But if I have a box, and I'm not going to make it very big, and let's say that this box is 3 by 2 by 3. All right, and let's say it's feet. Okay. Well, what this really means is I have 3 rows of 1 foot. So each one of those rows right there is a foot high. And then I have 3 right here. And then I have 2 deep going on the width back there. So basically what volume represents, volume is the number of cubes that would fill up the shape. So this cube here, there's actually, it looks like there's 6 on this bottom row. There's 6 there, and there's 6 here, and there's 6 on the top, for a total of 18, which is the same thing I get if I go 3 times 2 times 3. All right, so there's 18 feet cubed, or cubic feet. A lot of things are sold like that. Like I'm pretty sure my refrigerator is like 26 or 28 cubic feet, and a lot of times you'll see it written as cu.ft. So freezers and refrigerators are sold on cubic feet. Sometimes when you are building and you want to install like a gas fireplace, there's usually a certain amount of cubic feet that has to be in the room to support the fireplace. So it has a lot of applications in building as well. So let's try to do this little tent over here to the side. So we got a triangular prism. So I'm going to go ahead and kind of put a little line there to separate these two. Triangular prism. Now the first thing I need to understand is, if volume is base area times height, I have to identify who is the base area. And remember, for it to be a prism, the base area has to have a top and a bottom, and they have to match. They have to be congruent and parallel. So in this picture, the base area is actually that triangle right there, and this triangle right here. So for the base area, it's a triangle, and then the height is the distance between the two triangles. So let's kind of break this down. The area of a triangle is 1/2 base times height times the height of the shape. Maybe I'm even going to call this big H. That might be a little bit better, because you have the height of the triangle, which I'm going to call little h, but then you have the height of the prism, which is big H. So here we go. So we have 1/2. Well, the base of the triangle is right here. That's 3. The height of the triangle is 5. And the height of the entire prism, well, that's basically, I'm going to go, this is one base, and this is the other base. So the height is the distance. It's how far those bases are apart from each other. So this is my height of the prism. Okay, it has a height of 8. I think this thing would have been better had it been drawn a little bit more like up and down, instead of on, when it's sitting kind of down like a tent, it's not resting on its base. I think it's easier when it is resting on its base, but hey, that's life. Sometimes pictures don't work out the way you'd like them to be set up. Alright, so this comes out to be 3 times 5 is 15. 15 times 8 is 120, half of 120. I believe this is going to be 60 cubic inches, or inches cubed. Let's just double check this to make sure. 0.5 times 3 times 15 times 8. Whoa, what did I do there? 0.5 times, oh, I messed it up. 0.5 times 3 times 5 times 8. 60. Yep. Just double checking. I know you guys will call me out if I make a mistake and have a wrong answer on there, which is good. You guys should call me out. Alright, straight up cylinder. Let's get after this. Volume is the base area times the height. I'm gonna use that capital notation from now on. So the base area is actually a circle. So it's pi r squared times the height of the cylinder. So the radius is 8. So I have pi 8 squared times 10. So 8 squared, that's 64 pi times 10, or 640 pi. Now that's exact. If I want to leave it exact, I can leave it there, call it millimeters cubed, and just call it a day. If I want to approximate it and get an actual real number that's a little more meaningful to me, I'm going to multiply it using the pi key. all your calculators pretty much should have a pi key. You can use 3.14, but the pi key is a little more accurate. And that's about 0.62 if I round it correctly. So either one of these answers could be fair game for a test of mine or a standardized test. Alright, so there's volume of a cylinder. Now this next one's kind of interesting. The next one over here, it's basically got two shapes to it. So picture if I kind of poured some water in, right here. I want to know how much water that shape right there could hold. And there's a lot of parts and things in the real world that aren't just one nice shape. They're kind of complex and they have different pieces to it. So I think to get the volume of this entire shape, I need to do the volume of the box and add to that the volume of the cylinder. And so these aren't too bad. Remember, the volume of the box is just length times width times height. The volume of the cylinder is pi r squared times the height. Now these two h's are going to be different though, because this height represents the height of the cylinder, where this height right here represents the height of the box. So you have kind of two different h's going on there. So let's go ahead and let's break this down. So length times width times height plus pi times the radius is 2 squared times 4, and that's 150 plus that 416 pi. Now I have seen on ACT tests that they'll leave the volume just like this. They'll just leave that expression. You can't put 150 and 16 together because it's tied up with that pi. So you can't call it like 166 pi. That wouldn't work. You could only add pi's with more pi's. But if I want to actually get a nice decimal that has a little more meaning, 150 plus 16 pi equals, I get about 200.27, and we're talking meters cubed or cubic meters. So this is the approximate value. Alright, let's keep on going. And let's move on down. And this is kind of a bigger concept here, so I want to kind of highlight this because this is often tested and it's kind of a big idea. Maybe I'll put a little light bulb kind of looking thing there. So it says find the volume of the prism below, then double all dimensions and find the volume. How many times larger? So I want you to kind of make a prediction. I'm doubling the dimensions. Okay. So what I'm going to do is I'm going to take all the dimensions, meaning the length, the width, and the height, and I'm going to double them, or I'm going to multiply by 2. And what I want you to try to figure out is, when you do the volume, what do you think is going to happen? What does it get multiplied by? Does it get multiplied by 2? Does it get multiplied by 4? How much bigger, how much more can it hold? If I have a box and I double all the dimensions, how much more stuff can I put in it? So let's kind of get after this. So the volume for the shape as is 7 times 2 times 5, length times width times height, for a grand total of 70. So 70 cubic inches. So there's my volume, 70. Now, if I double all the dimensions, okay, and I redraw, this box over here, and he's bigger. I didn't quite make it to scale, but if I double everything, that would be 14 by 4 by 10. So I basically times every number by 2. Well, over here when I do the volume, I'm going to get 14 times 4 times 10, which is going to be much bigger. It's going to be what? 140 and 4 is 280, 560. Whoa. So look where I started and look where I ended up. Now, how many times larger is the new volume compared to the old. Well, if I do 560 divided by what it used to be, I'm going to find out it is 8 times larger. Okay, 8 times larger. So when you double the dimensions, it's 8 times bigger. Now those two numbers are related. You know, if I double the dimensions and I got 8 times bigger, all right, these are the dimensions and this is the volume. The only way to make that 2 turn into an 8, and this is the whole key right here, it's to the third power. That right there is the big thing you need to understand. Whatever you do to the dimensions, you raise that to the third power to do the volume. So for instance, if the dimensions are 4 times bigger, the volume is going to be 4 to the third times bigger, or 4 times 4 times 4, 64 times larger. So if you increase all the dimensions of a box by a factor of 4, it can hold 64 times the amount that it used to hold. So that's the key, that's the bigger idea for today. Whatever happens with the dimensions, the volume is to the third power times bigger. Alright, so not too long in notes today. I think you got at least a start. You got enough to kind of get rolling on the practice tomorrow, and I'm sure you'll encounter some little nuances that we didn't get to in the notes, but that's what practice is for. See ya.